Proportion for the average path length. The average internode distance of NP cross MP 3ASL torus is as follows. L power 3T is equal to NP plus MP divided by 4 plus NP square divided by 12 MP minus 1 divided by 3 MP. If NP is less than or equal to MP, second NP plus MP by 4 plus NP square divided by 12 MP minus 1 divided by 3 NP minus NP minus MP the whole cube divided by 12 NP into MP else. Proof. Since the topology is node symmetric, we assume S1 equal to 1, 1 is at the center of the torus. Then the torus can be divided into 4 similar parts. First, we focus on the right upper part where the index satisfies these conditions. Then according to when del h is del h of v comma h is equal to 0 as the black nodes. When v is less than h minus 1, del h of v comma h is equal to h minus v minus mod of h plus v comma 2 as the gray nodes. Then the sum of the extra required hops in the pod is summation sum of del h of v comma h is equal to sum of h is equal to 3 to np divided by 2, sum of v equal to 1 to h minus 2, h minus v minus mod of h plus v comma 2. Similar expressions in the other three parts can also be obtained. Then for the whole network we have the following equations based on the average internode distance of 4 ASL torus. Its total internode distances is then the total internode distance of the 4 ASL torus sum to this expression. Finally, according to ninth equation, the proportion is proven. According to proportion 4, comparing to 4 ASL, we find the average distance of the 3 ASL torus is increased as follows. When NP is equal to MP del L, which means that the average distance of the 3 ASL torus del L equal to 0.08 into NP, which means that the average distance of the 3 ASL torus is slightly increased compared to 4 ASL case. However, when there are too many orbital planes, the increased distance becomes more relevant. When NP is greater than MP, del L is approximately equal to NP by 4. Furthermore, since the average of the interplane ISL are both NP by 4 for the two topologies, we can obtain the average hops of the interplane ISLs. L intra power 3t is equal to L power 3t minus NP by 4. To sum up, 3 ASL topology differs from typical 4 ASL topologies primarily due to additional detours incurred when there are numerous interplane hops. Lemma 1 delineates the calculation of these extra hops. Subsequently, proportion 1 and 2 provides an explicit formula for the hop count in 3 ASL mesh and torus topology respectively. Based on this, corollary 1 quantifies this increase in hop count relative to typical 4 ASL configurations. Finally, proportion 3 and 4 determine the network diameter and 8 for 3 ASL torus respectively. Shortest routing discovery in the 3 ASL topology. The last section focuses on the routing metrics for the overall network. Then this section studies the routing discovery issue for the specific source and destination satellites. The 3-acyl topology is further converted into honeycomb pattern. The path searching region and path diversity are formulated. The shortest path between the two satellites are not unique, and the nodes on this multiple potential shortest path form an SPSR. A node belongs to an SPSR if and only if it is an element of the some shortest path between the two satellites. When SPSR is determined, the shortest routing discovery becomes more efficient. Given the source satellite and destination, it can be known that for any intermediate satellite within the SPSR, the sum of the distance towards SC and the SD equals to the distance between SC and the SD. That is, if SI is less than if SI is a set of SPSR, then H of SC, SD equal to H of SC, SI plus H of SI, SD. For a better illustration of SPSR, we convert the network topology from the brick pattern into honeycomb pattern. The interplane ISLs are staggered and tilted, forming a hexagonal honeycomb pattern. A triple indexing scheme is introduced to facilitate the formulation of SPSR. Let the origin 0, 0, 0 be at the satellite at node 1, 1 and let x, y and the z axis are to be parallel to 3 edge directions respectively. The x-axis points in the direction where the satellite v-index decreases. The y-axis points in the v-index increasing direction, and z-axis points in the h-index increasing direction. Then all nodes with a fixed x, y and or z coordinates belong to the zigzag chain. Then based on the indexing rules, the index of the neighboring satellite can be given. Given as follows. Note that the index formation only works in a mesh topology. With a triple index, a honeycomb pattern is formed and its topological properties can be derived similar. The distance between SC of x, is x1, y1, z1 and SD of x2, y2, z2 can be concisely given by h. Then the hop count in the 3-acyl mesh topology can be calculated as follows. The above equations indicates the shortest path between the two nodes along the x-axis and along hops along y-axis and hops along z-axis respectively. Then the SPSR can be specified by a group of several continuous hexagons. The SPSR then the SPSR is limited by 6 zigzag chains given the source satellite and the destination satellite. For any intermediate satellite, source and destination for intermediate satellite within the SPSR. Shortest path diversity. The shortest path with minimum hops is not unique in 3-acyl topology, is confined within the SPSR. The shortest path diversity can be calculated with del x, del y and del z. Proportion 5. The number of different shortest path between the two nodes in 3-acyl topology is as follows. The forwarding hops cannot be consecutive. For example, after a hop in x direction, the next hop must be along either y or z direction, and similarly for the other two directions. Assuming that z direction has the most hops, then it must be the case that del z minus del y plus del x equal to 0 or 1. On the other hand, the shortest path has total hops before and after del z hops in the z direction, and there must be one hop in the x or y direction, which accounts for del x plus del y hops. Therefore, each path can be determined by simply deciding the positions of del x and del y the x direction and y direction respectively. Then the total number of different paths satisfy other numerical relationship. This pattern also hold true, thus proving the proportion. The three cases of path diversity in SPSR, we find that x1 and x2 is just the number of involved hexagons. Note that SA or ST is near the marginal in 3ASL mesh. The path number will be reduced because the SPSR hexagon are truncated, but there is no marginal area in the 3ASL torus. Then the above equations are more suitable for two nodes are not too far apart in 3ASL torus. Thank you.